那边有位置。
等一下遇到学生哈，工作人员学生，然后我跟他们请他们帮我一个忙，因为我那个9点的电视学的课，我昨天虽然有讲，但是因为我怕有些人又跑去那个教室，在603教室，就说今天电视学的课来这边参观比赛，
可没有位置
啊？没有，他讲他们不会来的啦，对呀。但是9点，但是因为我找不到工作人员，你如果看到帮我讲一下。
Good morning, ladies and gentlemen. It's already time for the PYCT 2025 final Physics 5. Today we have 3 teams for our Physics 5 who are the highest scores in the past 3-day fighting. So we have 3 teams who are grounders and empty joker, and last one is the without male end. Okay, so I would like all 3 teams to introduce them. I think from reporter.
I'm the leader of ND Joker, and I'm 谢婉瑜、于晨杰、庄真、黄义恩、许哲瑞。
And followed by opponent.
Good morning. I'm the leader from the team without male end, and I'm Chen Ziqian. This is Chen Xinyi. This is Huang Yanzhen, and this is Luo Yongqi, and this is Huang Yizhou.
And finally, would be the background check.
Good morning, everyone, and I'm the leader of the Avengers team, and my name is Andrew Lee, and this is my teammate Jeremy, Wayne, James, and Cody.
several honored jurors. So I would like all the jurors to introduce yourselves briefly to the audience.
Good morning. My name is Chen Hongyi from National Taiwan Normal University.
Retired from Zhongzhen University.
Retired professor from Intermission.
Good morning, everyone. I'm Jiasidang. I'm a retired professor also from National Taiwan Normal University. Okay, another retired professor, from National Taiwan University.
Good morning, everyone. I'm Cai Zishen from National Taiwan Normal University.
Good morning, everyone. I'm Zhe Yonghong from Hankai University.
Good morning, I'm Wen Qingling from NTNU.
Hello, good morning, everyone. I'm Zhang Yuzhen from Foreign Catholic University.
Good morning, everyone. I'm Jinghua Lu from NTNU Physics.
I'm the last one. I'm Yongren Xu. I will be the chair of this physics fight. And following, we will have the fight soon. But today, in the physics fight, all the problems were pre-selected by the presenting team themselves, which is different from the normal physics fight. The problem were challenging. So for the first stage, the reporter will be Andy Joker, the opponent will be Yingdao Mei An, and the reviewer will be Lagrange. And problem to be reported is number 7, ruler cannon. And then we start the preparation time for reporter, 5 minutes. So please start. At this time, I would like to remind all 3 teams, please write down the presenter's name on the whiteboard. Okay, it's almost time, so reporter, please start your report. The time is 12 minutes.
Good morning, honorable judges, partners, and competitors. I'm the reporter from MD Joker. The topic I'm going to present today is problem number 7, ruler cannon. Here's a problem statement. Two rulers are held tight against each other. A round projectile, such as a plastic balloon, peg, or a ball, is inserted between them close to one of their ends. When extra force is exerted on the surface of the rulers, the projectile is ejected at a high speed. Investigate this effect and the parameters that affect the ejection speed. And according to the problem statement, our main focus will be the relation between the ejection speed and the deflection coefficient, and also the relation between the ejection speed and the Young's modulus. And here's a demonstration video. We can see that when we give an extra force, the projectile will release forward. And here's a theory. Because the ruler is elastic, so the parameter that we can neglect is the deflection. So according to the universal theory, we can know that the bending momentum over the Young's modulus type, the second moment of inertia. This is a notice point that we want to mention. Is the second point of area. It's not a moment of inertia. And after 2 times of integration, we can get a deflection, which represents the vertical deformation, which means that if before I give a force, the ruler will be like this, and after I give a force, it will have a deformation from this point. So the unit of the deflection is the bend. But in our experiment, there are 2 effort points and 2 forces, so it will not be the same as the universal theory. And in our experiment, there are 2 effort points. So the effort point and the force will affect the difference between the deflection. And we can observe from the x1, for example. The total deflection of the x1 can be divided by the deflection caused by the f0 and the deflection caused by the f1. So the total deflection of the x1 will be equal to the deflection caused by the f0 plus the deflection caused by the f1. And why E can be plus together is because in our experiment, we put the projectile between 2 rulers, and it will give it a first vertical deformation. And after I give it an extra force, it will cause a second vertical deformation. As the graph we showed at the right. When I give the force and when I give the extra force, the contact point between the projectile and the ruler will move forward, which will be nearer to the fixed point, so the deformation will change. And we need to calculate 2 points to the total deflection. So the total deflection from the x point will be equal to the deflection 1 plus the deflection 0. And the difference between the deflection 1 and deflection 0 is that the force is not the same. The force of deflection 1 is the F1, and the force of deflection 0 is the F0. And from deflection at the x1, there will be deflection 1 plus the deflection 0 point. And the difference between the deflection 1 and deflection 1 point is their F4 point is not the same. And we plus two deflection together. And the place we want to mention is that it is not plus, it's minus, it's because the direction of F1 and F0 is opposite. So it will be minus, not the plus. So after generation, we can get the F1 and F0's equation. Then, according to the problem statement, the parameter that it wants us to do a comparison is the velocity. So we need to translate the deflection into extra force and the velocity. So we use F equal ma, and we put a sin theta cosine theta F0 into the upper equation. So we can get an acceleration. And in our theory, we assume that all work done by the ruler will translate into the kinetic energy of projectile. And also we consider the dynamic friction. But one thing we neglect is the heat energy that caused by the friction that we neglect because we think it's really small. So we can get the velocity. And one thing we want to mention is that in our experiment, we found that the contact point is from 12 centimeter to 30 centimeter. And in our experiment, the first thing we want to mention that is our theory and experiment is suitable. So we found an easy way to compare our theory and experiment. So the easy way to compare it is that the force that pushes a projectile forward will be bigger and almost equal to the maximum state deflection. So after generation, we can know that tangent theta is bigger and almost equal to the coefficient of state deflection. And we translate our tangent theta into the present of the delta and the x. So we can get the formula, this part. Then we do our experiment. And the data we measure is the delta x1 and the alpha point. And we can see that our theory is highly fit to our experiment. So we can prove that the theory can fit our experiment. So this is our experiment setup. The way that we give the force to the ruler is by the spring. So we can measure how much force that we give to the ruler. And the complex picture is to make sure that my projectile will eject forward horizontally. And for experiment 1, the independent variable is the x1. It is the error point, which is the length of x1. And this is the experiment data of our experiment 1. We can see that when the alpha point increases, which is the x1 increase, the initial velocity also increases. And this is a comparison between the experiment data and the theoretical data. And we can see that when the x1 is smaller, the error will be bigger. And this point we will discuss in the discussion. And for experiment 2, the independent variable is the radius of the projectile, which will change the deflection. And this is the experiment data of my experiment. We can see that when the radius of the projectile increases, the initial velocity also increases. And this is the comparison between the theoretical value and the experimental value. And we can see that when the radius of the projectile increases, the error also increases. And this part we will discuss in the discussion 2. And this is the experiment 3. In experiment 3, we change the material of the ruler, which will also change the parameter of the Young's modulus. And this is the parameters. We can see that our coefficient of state deflection and the coefficient of dynamic fusion is almost the same as each material. So the only things that we will change is the Young's modulus. And this is the experiment data in my experiment. And we can see that for the initial velocity, when the Young's modulus increases, the velocity also increases. And when the Young's modulus increases, which means that it's more hard to be bended. And this is a comparison between the experimental data and theoretical data. Also, the error between the experimental data and theoretical data we will explain later in discussion 1 and discussion 2. But this part we want to mention is that we can see the Young's modulus really measure the error. And for discussion 1, we want to discuss why x1 is smaller, the error will be bigger. This is a BP chart of my 6 centimeters data. We can see that in our experiment, there will be two sections of acceleration. For the first section of acceleration, the center of the mass is within the ruler. But for the second section of acceleration, the center of the mass is already out of the ruler. And this is the difference between our theory and the experiment. In our theory, we assume that when the center of the mass leaves our ruler, the ruler and the projectile will not be contacted, which means that the ruler won't give the projectile a force. But in our experiment, when the velocity is too small, when the center of the mass leaves the ruler and the projectile will still be contacted, which means that the ruler will still give the projectile a force. So we have the second section of acceleration. And we can see that from our experiment photo, that the center of the mass already leaves the edge of the ruler, and it is still be contacted. So after this, we correct our theoretical data, which would pass the second section of acceleration into our theoretical data. And we found that the last point of our experiment that had the second section of acceleration is a point at 9 centimeters. So the correction we only do from 6 centimeters to 9 centimeters. And we can see that the error highly decreased after our correction. And for discussion 2, we want to mention that why the radius of the projectile increased, the error increased. So we can see that in our experiment, the point from x to x1 is a curve, but in our theory, we assume that as a straight line. So we found that when the x1 is smaller and when the r is bigger, the error will be bigger. Then we modify our theory. We change a straight line into two straight lines to image it as a curve. Then we fix our theoretical data. And after fixing the theoretical data, we can see that our error percentage also decreased, so which means that this correction is right. And for experiment 2's correction, we can see that the error also decreased, so which means that it fits more. And here comes our conclusion. In our experiment, when the F1 point and the fixed one is further, which means that x1 is bigger, the injection speed will be faster, and the radius of the ball is positively correlated to the injection speed. And also, the Young's modulus will be positively correlated to the injection speed, which means that when the ruler is more harder to be bent, the initial velocity will be faster. And in our error part, we found that when the F4 point and the fixed point is further, which means that the x1 is bigger, the error will be smaller. And when the radius of the projectile is greater, the error will be greater. And also, the Young's modulus didn't really measure our error. And here's the conclusion from our discussion. The projectile gets a second section of acceleration when the velocity is smaller than the speed at which the two ruler goes. And the second section's acceleration will matter more when the third point and the fixed point is nearer, which means that x1 is smaller, and when the radius of the projectile is larger. And also, the error caused by the grammatical approximation can cause the theoretical data to be smaller than the experimental data. And the error caused by the grammatical approximation would matter more if the error point and the fixed point is nearer, which means the x1 is smaller, and also if the radius of the projectile is larger. Here's my presentation. Thanks for listening.
Okay, following is the time for the opponent to ask questions. So please start your questions.
For a reporter, you have mentioned that there are F0, F1, and X0, X1, and delta X1, delta X0. So which is the constant and which can change when the projectiles, which can change in time? In your experiment.
In my experiment, when the projectile is ejected forward, the parameter that will change is the F1, but it won't change a lot.
Okay. And so the opponent suggests that you can mention it clearly. And the next question is, can you see the definition of the I index that you mentioned is like the second moment of area?
Okay, the second moment of area is different from the moment of inner shaft is because it doesn't matter from the density, and it's according to the cross-section area.
Okay, we will discuss this part later. And then the next part is that you mentioned that if we change in your third experiment, you mentioned that if we change the material, only the Young's modulus will change, but you can mention the friction. So you mean that if I change the material of the rulers, the coefficient of friction is like static, or?
I have mentioned in my prerequisites, the coefficient of static friction and the coefficient of dynamic friction is almost the same, so which means that it won't change of our friction and dynamic friction.
Oh, okay, I got it. And my next question is, do you think the material and the length will have like the cross influence, or it will be like the individual?
And you mean the material of the ruler or the material of the ruler?
The material of the ruler and the point that you affect your force, like these two variables.
Now stop. Please answer. Hello. Reporter, can you answer in short?
The upper point and the Young's modulus is a different parameter, so we can put it together in one experiment to do a comparison.
Okay. Thank you. Now is the time for opponent's preparation. Okay, it's almost time. So opponent, please start your position. You have 4 minutes for presentation, and any remaining not used time will be added to the discussion.
Good morning, honorable judges and fellow competitor. This is the opponent Chen Ziqian from Yunnan, and today I'm going to oppose the problem number 7,徐有庠. And the main focus of the reporter is the deflection coefficient, which means they changed the Young's modulus, and the second, and there's the overview of the report. In the theory, the reporter mentioned the unilateral leading theory and the deflection which is caused by the deformation. And they also talk about the stacking of the deformation when the force is applied at 2 points. And about the experiment, the reporter mentioned the force application point to the inertial velocity and the radius of the projectile to the initial velocity, and they changed the Young's module of the rulers and to the initial velocity. And about the Young's modulus here, they changed the material of the ruler, but about just changing the Young's modulus, and about the friction, they have found the same friction of every type of the rulers. And the conclusion of the reporter is a projectile will get a 2-section acceleration if the initial velocity is smaller than the speed at which 2 rulers closed. And the 2-section acceleration would matter more when the 4-point and 6-point is nearly, and also when the radius of the projectile is larger. And there are the pros and cons about the report. I think the report has a clear data elaboration and they have precise conclusion. But I think the cons about the reporter is they have the unclear observation, which I can see about the demonstration video. That is like all black, and I just can see a white things like flying away, and they have lack of clear definition of every sign. They didn't mention clearly, like, I don't know what is the delta 1, delta 2, and delta 1 plum, delta 1, delta 2 plum, and delta x1, delta x2. They didn't mention it clearly. So this is a bit confused to me. And there are points that we are going to discuss about the theory. About the theory, the reporter mentioned the definition of the I, which is the second moment of the area. But according to what I know about the reporter use the I is they use the I is equal to BL's cube over 3. But about my opinion, this equation is only when the beam of the ruler is like straightforward. And I'm going to discuss on the successful ejection condition, which is the theta. I think the reporter didn't mention it clearly, and the rotation through the process. And there are 2 parameters are changing. The independent variable. Just forgive me. And the experiment, I have to discuss on the material to the length, and the second one is about error analysis. But because the report didn't really quantify the error, so if the report just mentioned as a small that's a minor effect, like about 5 minor effect, is there going to stack into big effect? This is the point we are going to discuss. And let me invite the reporter.
Okay, please start the discussion.
Okay, the first question is, I'm going to ask you to show again the I index, which means the second moment of inertia.
Is that?
Yes.
You want me to explain the second moment of area?
Jury, can I use the board? Let me show you. Sorry. Can I just write how can this equation of I get? Like when there's a thing over here, and this is the and this is the x-axis, and this is the y-axis, and the ruler or the thing is over here, and this is the point where it fixes, and then we'll have normal deformation. And if I want to calculate the second moment of inertia here, is equal to the x and y. And here is for b, or for width of the ruler and for length of the ruler. So the second moment of area is equal to like this.
So you won't mean that this using that is not meaning the ruler can be bended?
Yes. According to, can you show that page? The page that you turn. No, it's this part. As you can see here, the door is bending like a very big. It is bending like a. It has a very big bending, and this equation, I have proved that, which can only use at when the door isn't bending. So the opinion of the opponent is you have to calculate the moment of inertia by another way. I think this is the point that I suggest you to do.
In our experiment, we use this formula to measure our Young's modulus, or we want to measure the Young's modulus of our material. And also we use this to represent the deflection. So the main parameter that we want to say is the deflection. And I think the error that you mentioned is that only when I'm measuring when I'm measuring the Young's modulus. When I'm measuring the Young's modulus, the ruler can be bending.
Okay, I got it. So let's move on to the next question here. Please turn to the experiment 1. Experiment 1. The data of the experiment 1. Can you show the theoretical data? No, yes, this one. So can you explain why the slope of the curve is like increasing?
You mean the theoretical line? The
Yes.
theoretical line is according to our experiment. Is according to our theory.
So you mean that you can explain why the slope is like the
Explained by our equation. We have the equation for our theory. From this part, we can see that the v will be affected by the parameter, and from the x, the parameter that we change in the experiment 1 is the x1. So when x1 changes, the v will change, and the trend is caused by the formula. I put the data into this formula, so it round this trend for me.
Okay, I got it. So can you stay on this page? So like this equation here, which is the value that you will change by times.
You mean the value of the...
No, like this, like there are many
You mean the
coefficients.
parameter that will
Yes,
change by
that will
times?
change by times.
The parameter that will change by times, the first parameter is the x0, because my projectile is ejecting forward. So the contact point of the ruler is changing.
So you mean there are only the x0 will change by times?
Also, the f that the projectile is ejected is exerted will change also.
You mean the f0 and the f1 will change?
The f1 is the force that I give to the ruler. I'll give the same force.
Okay, so can you turn to a page of the equation that you solved the f1 that means you apply your force. Can you turn to that page? You have solved and like a linear equation in variables. Yes, this one. So you mentioned that the value of x0 will change, but the f1 will still be constant.
I mean the f1 will be constant in my experiment. When I'm doing the experiment, I remember
So you say that your experiment isn't fit to your theory?
We have because we know that it's an assumption, so we have measured before the f1 of the parameter that will change, and we found that when it's from the top, the projectile is at the top centimeter to the 30 centimeter, it will not be the same, but the error of it is only 3.74%. So we think that we can neglect it.
Sorry, the suggestion of the opponent is this equation. You have the f1 on the right side and the left side. So I don't know what these equations stand for. So never mind that. Move on to the next question. So as you mentioned in your theory, the effect point is just like a very small point. But I see you mentioned that you use a spring that is fixed on the nuclear. So the spring I found that there are a very big area that is fixed on the nuclear. So is this will fix to your like this will fit, or you have calculated deviation?
In my opinion, the area of the spring and the ratio between the area of the spring and the length of the ruler is about only 25%. It's not a half. So we think that it won't affect us.
Okay. So is there any rotation about the projectile?
We have in our experiment there were gravity, so the N1 and the N2 won't be the same. And the difference between the N1 and N2 is 0.198.
So which do you think will cause the rotation?
Let me finish.
Okay,
and
sorry.
So we need to calculate the friction between the difference fraction between the lower part and the upper part. So we found that the difference between the friction is only R plus 0.03564. It's really small. So, and also in our experiment, when we are observing the demonstration video, the rotation won't rotate a lot. It's almost smaller than 5 degrees. So we think this is negligible.
Okay, so you think what caused the rotation? Which force? Can you just tell me which force?
If it will rotate, which means that the friction upper part and friction downward part is not the same.
Okay, but from now on, you have measured like your deviation, maybe the friction, and there are the there are the I index and the friction, and you have said that the arc length of the ruler can be equal to the linear distance, and you have there maybe have some air resistance. So if you think if I adding this deviation together, I will get a very big deviation. If there okay.
We think the deviation between the caused by the air resistance is small. We have calculated the air resistance how many it will affect to our experiment. And after our calculation, we can see that
sorry, you misunderstand my question. My question is, when after I adding the every deviation together, will it become a big deviation? If you calculate it, yes.
This deviation that it really can be divided. We proved that it can be negligible because by our experimental data.
Okay, so the opinion of the opponent is that you have to calculate all of the deviation of different things like E index or whatever, but you didn't do that. You can do it furthermore. And so let's move on to the next question. Let's move on to the next question. So you mentioned that there are two segments of the ruler, right? If there is applying two force, there are two segments of the rulers, right? The ruler becomes two segments of the bending. So do you think that each two segment is like a uniformly bending? Like after differentiation, it will become after differentiation twice I can get a constant. Do you think it's like this or what?
Can you repeat your question again? I don't really understand.
Can you support? Like the ruler you use is like this is the first bending and this is the second bending. Well, like two segments of the bending. So we'll think like this type of bending is like a uniformly bending, and this is a uniformly bending.
But in our experiment, the bending that
can you just answer my question if there is a uniformly bending?
But this part we won't consider in our theory and experiment. We only consider this part in our experiment theory, and we also do the correction.
Okay, whatever. Just move on to the next question. Sorry. And this is all my question.
Okay, time is up. So following is the time for opponent to make your discussion summary for 1 minute.
Okay, about what we discussed about the recorder, I have mentioned that there are like many minor deviation, but I think that if I adding this minor deviation together, it will become a major deviation. So I think the recorder can ignore it. And the rotation is caused by the friction difference from the upper and the lower part. But the reporter mentioned that the difference between the normal force is like pretty small, and this point I agree with the reporter. And I have discussed with the reporter if the uniformity bending of the ruler is right or is incorrect, and the possible deviation caused by the error system is negligible. The reporter didn't mention it clearly, and this is my presentation.
Okay, I would like to ask the reporter and opponent to stay on the stage. Opponent, please stay on the stage. And be ready to answer the question from the reviewers. Time is 3 minutes, please.
Okay, so what do you think are the key parameters? Yes.
You mean key parameter?
Of active ejection speed.
Just like the current statement says, that is the force that applied on the ruler. So if there is no force applied on the ruler, the projectile will be just stick in the ruler. So I think the main parameter is the force that applied.
Okay, thank you. What about you?
I think the main parameter is the deflection and the Young's modulus, and which causes the F0 that the force that the ruler gives to the projectile not the same, the force.
And so for the opponent, as we can see in the setup, a reporter uses springs as means of applying force, right? And so may I use the whiteboard? Thank you. So for this one, if we use a spring. So when we are using a spring, have you considered buckling and other parts of the spring? Like, do you think that buckling and other means of deflection shorts the spring will affect? And also, as we can see throughout the experiment, the spring itself will not only have buckling, but also the affecting point of the force will be not the same. What do you think about this?
I think there is still a big point that maybe they ignored it, like the gravity. No,
I'm not talking about gravity. I'm asking about the spring itself. I'm saying that the spring, the upper one and the downward one.
Yes, I say when the gravity, the upper one and the downward one, the depth will be like a bit difference with the gravity. Yeah.
I'm not asking this one. I'm asking on the bucklings. The bucklings. Okay, so as you can see on the spring, if we press the force, it will actually have some sort of buckling.
Yes.
And have you guys considered the bucklings of the spring?
In my experiment, I will measure that the buckling won't affect, and also the delta x, which means the spring's length change will be the same. The difference between there will not be difference between the delta x of the downward spring and the upper spring.
Do you know how springs work?
I know.
That if the springs were by the basis of the springs, when you have this compression and this compression, they will have drastically different force implications.
In our experiment, if it has this bend, if it has buckling, we won't use this experiment data, and the spring we use is not as long as this one.
How can you make sure there's no buckling?
I'll see in the video.
Time is up. So now, you have 2 minutes to prepare. preparation time is up. Please take the stage.
Greetings, I'm Tom Jackson from Team Lagrange's, and I'm the reviewer for problem number 7. So for the problem statement. And so the main focus will be the round projectile, extra force, high speed, and which is an ejection speed. And the force has not been mentioned throughout the experiment. And this is our outline. So the pros and cons of the reporter. First of all, the pros. The key questions are clear, and the clear theory deflection talks about the deflection, the elastic considerations, Euler-Bernoulli beam theory, force and force considerations. But for the cons, the spring is not uniform, and force application point and magnitude might change, and the angle of the force might change also, and the consideration of rotation is not mentioned. And no experimental videos, no methodology of data, and the method of uniform force measurements is unclear. And for the pros and cons of opponents. First of all, congratulations on a clear presentation, enough short questions, and a clear presentation. And for the cons, the discussions are not deep enough, and no clarifications regarding the experimental setup, and too much emphasis on the theory. For the questions and answers, we first talk about x0, x1, dx1, dx0, which one is constant, and the reporter answered by saying that f1 doesn't change much, though we think it's pretty unclear on what exactly are you talking about. And the questions and answers. The second one, they talk about definition of I index, which we think that the reporter can answer by being more clear. And also they talk about the changing of the material, the Young's modulus. And the reporter answered by saying the friction is almost the same. And us think that the methods of friction calculation is unclear. And for the next one, the material, the ruler, and the point of the force. And so the reporter told us that Young modulus and force point different parameter and cannot be uniform in one experiment. And we think that they could do experiments and plot number of graphs. And they also talk about another one about the I index during the discussion. And we think that the reporter's answer is contradictory with experiments where ruler bends, since it is the same as the experiment to calculate the Young's modulus. And for the next one, they talked about x1, f0, f1, f0 again. And so the answer is that f1 is the same force you give to the ruler. And you can, an error is so small we can neglect it. And we think that f1 will change in the experiment. And also, as we can see over here, the force applied will actually have some sort of canceling out. And they also talk about the rotation of the projectile. And the reporter answered by saying that the rotation is small due to the difference of friction. And we think that it's due to the non-uniform force applied by the spring that is used in the setup. And the videos are pretty much unclear. And they also talk about the minor deviations and major deviations, where the reporter answered by saying no. And the experimental results looks odd towards us. And for our questions, we asked about the key parameters, where the reporter answered by saying is the deflection and Young's modulus, and the opponent says the force applied on the ruler. And also we asked about the spring as means of the applied force and buckling, where the reporter say that buckling won't affect, and the opponent says yes and mentioned gravity. And we talked, and also I asked them that actual properties of the spring, where they say they don't take data into with buckling.
Time is up.
And that's for my report. Thank you.
Now, following time is the reporter's concluding remark for 2 minutes.
Okay, thanks to the opponent and the reviewer. Here's a concluding remark of my presentation. And first is about the experiment, the conclusion in our experiment. The echo point and the fixer is further. The ejection speed will be further. And the radius of the ball is consequently correlated to the ejector speed. And also, the volume of Young's modulus is positively correlated to the ejected velocity. And the projectile will get a second acceleration if the initial velocity is smaller than amplitude to the impulse. Error caused by the geometrical approximation can cause the theoretical data to be smaller than the experimental data. And the concluding remark for our discussion is that first thing is the minor deviation is including in our error bar. I want to explain this to the opponent, but the opponent said it's okay, never mind. And the rotation is caused by the difference between the friction on the upper ruler and the lower ruler. And we put a data to prove that the friction between these two parts is really small, so we think that it's negligible. And for the third is the F1 don't change a lot, and we prove it in our experiment. We prove it by we calculate from our experimental data. The error of it is only about 3%, so we think it's also negligible. And the demonstration video is unclear because we use a high-speed camera and it needs to be very bright. So even though we give it a very bright condition, but it's still very dark, and we will try to improve next time. And for last is that using a spring to measure how much force we use the spring to measure how much force we use. This is the reason why we're using a spring to give force to the ruler. And if the buckling happens, or the upper part and the lower, then the upper spring and the lower spring have the different length. I will not put this in my calculation of the experimental data, which I mentioned is the same.
Time is up, and thank you. I would like to ask all three presenters to get onto the stage. Now is the time for jurors to ask questions. So any question? Please.
Okay, I have a question. Since you have a PowerPoint about the neglecting the gravity equation, right?
Yes.
You have put the force analysis of this, right?
Yes.
Now,
it's fine.
let's look at it. Okay. Do you believe that this diagram is correct for the opponent?
You mean if you agree on this?
Yes.
I think if this section is like when the it didn't draw it pretty, so I don't know how to say it.
Okay. How about the reviewer?
First of all, I want to emphasize that this graph is pretty unclear, and I don't pretty much agree.
Okay. For the reporter, you said the N1 and 2 is different. Why?
Caused by the gravity.
Yes, it's caused by the gravity. But if I want to neglect gravity, how do I do the experiment? What opponent?
Maybe I'll do it like this way, or like the ruler will be projected up and down.
Okay. How about that?
I would like to suggest using a horizontal plane.
Good. Thank you.
Any other question? Yeah, please.
I have a question for reporter. As you shown in page 21, the evaluated the theory, the data from the theory looks like smaller than your experiment data. Do you have any comment on this?
Because the theory we haven't do the correction of the second section of acceleration. After the correction of the second section of acceleration, the theoretical data will be bigger. Because we correct the theoretical data in our experiment, the second section of acceleration would happen, but in our theory, we didn't put in the consideration. So after the correction, it will be more fit.
Yeah, but I see that even it's more fit, but it's still smaller than your experimental data. Is it?
Yes. We think that maybe it is because that we have a lot of assumptions, and our theory is we put our theory in an ideal condition. So maybe it's because of this.
Okay, and how about reviewer and opponent?
I would say I disagree as you can see over here, the theory have a lower prediction compared with the experiments, but this haven't even included the energy dissipation throughout. And even if they added the corrections, it is still lower than the experiments. However, this is from excluding the energy dissipations and other source from the theory. And energy dissipation will only make the value lower, not higher.
I have heard some part about the reviewer, but I have to say just as I mentioned, I have to say that there are many minor deviations, but all of the minor deviation recurrent just say it can be ignored. So as I said, if the minor deviation is after is after superimposed, will it become like a big deviation, like about 10% or like what? I think it is about the many minor deviations.
Any further question? Yeah, please.
To the reporter, can you show the page that you show us the time-dependent velocity? You show the two-stage acceleration. Now, I'm very curious about that. In the first stage, it's almost a constant acceleration because when your mass is leaving, that the bending angle is becoming smaller, the force should be smaller, and also the component should be even smaller. But why it looks like you are keeping a constant force or constant acceleration? Can you explain more?
We have to do a calculation. In our experiment, when the ruler and the projectile is contacted, the length is from 12 centimeter to 30 centimeter. And from this page, this is a force that changes if my ball projected forward. And we can see that it's almost the same. It won't change a lot. So maybe it's because of this, so the acceleration almost looks like the same.
Okay. So the force is coming from the ruler or is from the spring?
You mean the force?
Yeah.
It's from spring.
Okay, so I have the question for both of the other two. That you mentioned about the impact of the spring. Can you tell me like, what do you think about shortening?
Okay, so as I just mentioned about the gravity and support, like there is like the springs like this, it's like this way and it's like this way because it is like perpendicular to the ruler, but the gravity will pull it like this way and gravity will pull it like this way. So I think the gravity will cause that the gravity isn't just up forward the deformation, it will become like some just as the reviewer mentioned.
I would suggest that not only the F1 will have a canceling out operation, but also there are no two identical springs. And also the springs tend to be non-uniform during compression. As you can see over here, if we compress the spring,
please keep your answer short. Please keep your answer short. We are already over time.
Oh, so I don't really pretty much agree.
Is the force by measurement or by calculation?
And you mean the F1?
Yes.
By calculation.
Okay. Now we moving forward to scoring because the time is already over. Okay, I see the jurors are all ready. So please raise your score for the reporter. I will read from my right-hand side to the left. So the scores are 7, 7, 7, 7, 7, 8, 8, 8, 6, 7, 8. Okay. 6, 7, 7, 7, 8, 7, 9, 8, 7, 7, and 7. And at last, the score for the reviewer are 8, 9, 6, 6, 8, 7, 7, 8, 7, 8, and 7. Okay. For the reporter, the scores are quite even, so I think we can maybe kindly ask someone to give some comments. So any comments for the reporter? Yeah, please. Thank you.
I think it's much easier to do experiment. You use the dynamic method to do experiment. But it's like a spring. You have to do spring acting on the subject. You can use the static moment measuring. Of course, there's a problem because there is friction force. You have to resolve friction force. I'm not going to be the
And for the opponent, we have a 9 and a 2 score for 8, and several 7, and 1 low score for 6. So maybe for the 9 and 8, any comments?
May I?
Yeah, please.
I found out the opponent helped me to review all the concepts that raised by the reporter. So I think that's a very good way to be an opponent. And also, he challenged several problems very well and didn't give too much stress to the reporter. Okay, thank you very much.
Okay. And any comments for the low mark part? No. Okay. So for the reviewer, we also have 9 and 3 score for 8 and 2 score for 6. So any comments for low or high mark? I think for the 2, 6. So please give a comment.
I hear that you have many disagreement with the reporter or opponent, but by raising your short question, I feel like you are mostly focusing on the buckling of spring. For me, it's a little bit pity that you should spend more time on challenging more sharp question in different aspects. Yeah, that's why.
Yeah, please. Thank you.
Usually, as a reviewer, you shouldn't put too much of your own opinion on the reporter's work. You have to try to smooth out the conflict between observer and the reporter, and also try to extend your discussion to a more reasonable result. That's part of my comment. So I didn't give you very high score. I just give you 7. That's one of the reasons. Thank you.
Okay, I think that's all of the physics 5 round 1. So I would like to close this round and take a 10 minutes break. So please come back to see after the break. And during the break, please call 3 team to change your seat. Okay? 好， The break time is almost up, so I would like us three teams to get ready. Okay, I saw that all the jurors are ready. So I would like to start the second round. For this round, the reporter will be Dao Mei. Opponent is the Lagrangian, and the anti-joker will be reviewer. The problem to be reported is stripping faucet. Please start the preparation clock for 5 minutes. And during the preparation, all three teams please put the presenter's name on the board. Okay, now, reporter, please start your presentation. Time is 12 minutes.
Okay, so greetings to you, honorable judges and distinguished fellows of listening. This is YC from Randall High School, and today I'm here to present you with from 6 different functions. And this is my outline. And here is the problem statement. A living faucet develops interesting driven patterns where the time between drops depends on the water flow rate. Investigate this phenomenon and study how it depends on relevant parameters. So our main focuses are the driven patterns and the time between drops. And this is a demonstration video. So in the video, as you can see, the pattern of the droplets and the time between droplets are slightly different as time proceeds. So our presentation will be navigating how water flow rates affect the pattern of the droplets and the time between droplets. So let's go to the theory part. So let's talk about the shape of the droplet first. So this is a graph that we get from the paper we read down below here, showing the relationship between the lower H position and the volume of the droplets. So the solid line here represents the stable stationary states, and the red line here represents the maximum stable stationary dependent drops, which means that once the water volume exceeds this critical value, the droplet will flows. And the dotted line all above represent the unstable states, and since that the red line represent the maximum stable stationary dependent drops, those patterns on the dotted line will only emerge in motion. And we define the dropping condition as when gravity is larger than the surface tension, and we define the breaking point as the thinnest part of the water body where it has the smallest surface tension. And let's talk about motion after drops. So after the droplet falls apart, the remaining water up here, it will have a surface tension pulling upward, and it will try to reach an equilibrium with a viscosity which is striking down. So it will therefore cause a damping oscillation. And at low flow rate, you can see from this video, the impact of oscillation will vanish and go back to the solid line that I mentioned earlier here. So you can see in that small video, the oscillation is already reached equilibrium before another droplet drops. So the oscillation wouldn't affect both the pattern and the time between droplets. But at high flow rates, the impact of oscillation are yet to reach equilibrium, but another droplet already flows. So it will go back to something like that I mentioned earlier, and you can see from the video, before the oscillation reaches its equilibrium, another droplet is already flows. So that therefore will cause the difference in both pattern and the time between droplets. And so this is, so according to the paper we read, this is the so-called chaotic phase. So let's talk about the chaotic system definitions. So we'll be focusing on the first one, that the whole system is sensitive to initial condition because it is observable in the physics system, and the rest of the definitions are usually discussed in math. So according to the paper, if the system is chaotic, we should see a bifurcation diagram like this one down here. And we further break down this bifurcation diagram into this one. So it shows the relationship between the flow rate and the time interval between droplets. And it has a critical value to separate the whole system graph into linear system and nonlinear system. And we further use the Navier-Stokes equation to describe the motion of the fluid. So this is the resultant body force of the fluid. So we have the density times the local acceleration plus convective acceleration will equal to the resultant force caused by the pressure difference, gravity, viscosity, and surface tension. And as you can see, the second term, which is the convective acceleration, is a projected term. So when it is not equal to 0, it will make the whole system become nonlinear. And about this second specific term, when the convective acceleration is not equal to 0, the velocity will vary with position, as you can see here, because it has a convection going backward, or reduce the velocity around the central point from here will be like this one. So as when the convective acceleration is close to 0, it wouldn't cause a lot of effects on the velocity around the central point. So the velocity doesn't really vary with the position, and it will make the system linear just like this one. And here comes my experiment part. So this is my setup. So first of all, I have a bucket with adjustable faucets, and so how I conduct my experiment is that I open up the faucet in a second period, maybe like 7 seconds, and I collect the water with the measuring cup down below, and I further measure the net weight of the water that I collected in this fixed period with my electronic scale, and through further calculation, I can get my flow rates. And about the tracking of the time interval between droplets, I use a foam which is in slow motion, and I further put it into tracker to get the exact time interval. So this is how I calculate my water flow rates. So first of all, I get my net weight of the water that I collected in like the fixed period, and then I divide it with the time that experienced. Then finally, I can get my flow rates. And about the determination of the faucet radius, which would do the prerequisite experience like in with three kind of radius. So as you can see in your lab, when the radius is way larger than the droplet radius, is presenting a kind of like messy or predictable dripping patterns. And on our opinion, I think the water doesn't fill the whole faucets. So therefore, I think it kind of contradicts with the purpose statement that what a liquid faucet should be. When the radius is way small, the surface tension applying area is really small. So I think it will cause the limits in observation of various phenomena. So we choose the one that has similar radius with the droplets. So this is my experiment one. So my independent variable is water flow rates, whereas my dependent variable is the pattern of the droplets. So as you can see in the low flow rates, the pattern of the droplets to be the same as low flow rate since the balanced damping oscillation that I mentioned earlier. So it already reaches equilibrium, so it doesn't affect both the pattern and the interval. The high flow rates, as you can see that the droplets tend to be different at high flow rates since the impacts of the damping oscillation. Yeah, and we further do the discussion of this one. Though the first drop looks similar to the second drop, once there is a slight difference, it could bring about the variation of the next drop, which corresponds to the definition of chaotic system that I mentioned earlier, that the whole system is sensitive to initial condition. So once there is a slightly difference, it will cause the difference in next drop. And about my experiment 2, my independent variable is still water flow rates, whereas my dependent variable is interval between drops. So this is our data. So first of all, with this line, you can see that the flow rates, as the flow rate increases, the interval will decrease. And if we look closer to this part, and we enlarge it at this one, you can see a clear bifurcation on this one. And we at this certain flow rates, it can correspond to several kinds of interval, which we call it the chaotic system, chaotic base of it. And we'll further do our comparison between our experimental data and the bifurcation diagram that I mentioned earlier. So we all can see that we have a critical value which is between 0.2 to 0.3 grams per second, and marking the transition from the linear system to the nonlinear system. And here is my discussion part. So at this certain flow rates, you can see that it has two certain time interval, and after we conduct our experiment, we use tracker, right? So after we gather the whole time interval, we found out that there are only like two kinds of interval intertwining in the whole driven period. So we define this phase as double drip phase. And this is the video showing you that. So in this video, you can see there are two kinds of droplet patterns and two kinds of droplet interval, and we use tracker to further to testify that our assumption are right. And about the discussion of oscillation period at low flow rates, so we also use the tracker to get the period of the damping oscillation. So on this graph, you can see at around 0.2 seconds, the damping oscillation reaches equilibrium, which means that the period of the damping oscillation is around 0.2 seconds. And so when the dripping period is larger than the damping oscillation period, the damping oscillation will reach its equilibrium before another droplet drops, proving that oscillation does not have effects on the droplet post-droplet interval and the pattern. So, and we define it as the periodic phase. So here comes my conclusion for experiment 1, that patterns of the droplets tend to be the same at low flow rate since the balanced damping oscillation, and the patterns of the droplets tend to be different at high flow rate since the unbalanced damping oscillation. And the pattern of the droplet in the chaotic phase is in relation to the former drop since that the whole system will be sensitive to initial conditions. And this is my conclusion for experiment 2, that interval decreases as the flow rate increases. And in chaotic phase, at a certain flow rates, there can be several corresponding intervals. And we have the critical value is between 0.2 and 0.2 to 0.3 grams per second, marking the transition from linear system to nonlinear system. And based on the linearity of the entire system, we can further classify the dripping states into periodic, double drip, and chaotic. And this is my presentation. Thank you for your attention.
Okay, thank you. Now is the time for the opponent to ask short question.
Okay, so my first question is, how do you control hydrostatic pressure to make the flow rate constant?
Make the flow rate constant?
Yeah,
how the pressure of the water buckets affects my flow rate? Is that what you want to ask?
No, I mean, how you control the flow rate to be constant?
The flow rate is not a constant, like as I stated. The flow rate
Forget it. Then what about the ink you add to the water? Does it affect the viscosity in your theory?
Yeah, so basically the ink you see is green. It's only for demonstrating. So we conduct our experiment with pure water. So there will be no difference in viscosity.
Okay, did you account for the size of the drop?
Yeah, we do. We use tracker. We use tracker. So as I mentioned, so I determined that the function radius is close to the radius of droplets. So basically, we use tracker to get the instant before dropping, and we can get so the instant before dropping is the biggest. Is when the droplet has the biggest radius. So we use tracker to get the radius of it.
And can your Navier-Stokes equation predict the different like drop shape? Navier-Stokes equation. Can it predict?
It could just tell us that if there is a convective dispersion of exists, and further we can discuss how the system is linear or nonlinear. So it just helps us to understand.
Okay, so only distinction between linear and nonlinear. Then do you have a model for the nonlinear part?
Model? What kind of model are you?
I mean, theoretical model. So, for example, can you predict the time interval for higher flow rates?
No, we can just predict it to be there will be several kinds of intervals, so we can get exact value of it like just beforehand.
Okay, then if you do experience like increasing the low flow rate to high flow rate, or if you do experience to decrease the flow rate from high to low, does it affect the results?
Definitely.
It's okay. I'll clarify this.
Time is up. So you have 3 minutes to prepare. is about time. So opponent, please start your presentation.
Okay, so I'm the opponent for problem number 6 from Team Lagrangers. And today, so first the problem recap. The problem statement explicitly mentioned that they should focus on the relationship between the time between drops and flow rate. They did use their equations or to consider the low flow rate part, but they didn't investigate the high flow rate part, which is where the chaos begins. They should also focus on that part of the phenomenon. For the task, they identify the relevant parameters affecting drift intervals. However, the comparison between model and experiment is also limited. First, let me talk about the general pros and cons of the reporter. Well, they do have a well-organized report and they have a clear exploration of possible parameters. They also have a clear experimental videos by colorizing the fluid, and they classify the hang drop into different configurations for the low flow rate. They also analyze the low flow rate part as pen drop, and they use Navier-Stokes equations to describe the fluid phenomenon. For the cons, well, I think they should clarify the assumption first before using the equation, and the chaos system also needs to be deterministic. That is a part of the definition part. They also did not use quantitative explanation to describe the high flow rate, like how the drift interval will be affected by also other possible parameters. And they did not use their model like Navier-Stokes equation or the bifurcation diagram to predict the experiment. They also didn't give me a clear answer on how the flow rate is controlled, and they don't have, I think they don't have enough contribution to the field, so they only use like the results from the research paper. And they also did not explain the boundary of their model and how in the end of the process, which is the necking, the fluid dynamics is determined. So first, let me talk about the report. Well, in the preliminary experience, they have an observation of the phenomenon and how the different radius of the faucet will affect the dripping pattern. But they only observed the phenomenon and possibly gave some qualitative explanations of that the radius doesn't really affect it for low flow rate. And for the modeling part, they used Navier-Stokes equation, like that, and to describe it. However, it only predicts when the nonlinearity will occur, but did not predict other factors such as the dripping interval, as mentioned in the problem statement. And yeah, and they didn't have an unclear modeling of the chaotic system. Yeah, so now next for the experiments analysis, they did 3 experiments in total, I believe. The radius of the flow rate, the damping oscillation, and the radius of the drop. Well, in the first part, they changed how the radius of the faucet, and they found that for high flow rate it is different. And they also did experiments on the bifurcation diagram to describe the data, and they also compared double dripping and other dripping patterns. However, they did not include the drop size calculations, which I think is very important in the fluid dynamical part of the theory. And they also defined periodic phase. However, they have no comparison between theory and experiment, and they did not describe the non-linear part of the system. So my major discussion points will be the force analysis, which is how the force is acted upon the droplets, and the definition of high or low flow rate and the assumptions. I will also talk about the stable flow rate control, or the flow rate from high to low or low to high, and the parameters to explore, such as surface tension. And for the data analysis, I will also talk about the bifurcation diagram.
Time is up. So,
thank you.
Porter, please get up to the stage, and we start the discussion for 10 minutes.
Okay, so my first question is, can you describe the force acting on the drop before it falls, like the pendant drop? Okay. Well, I think you should also include Yeah, so I think you should also include the liquid flow from the momentum of the liquid flow. I think it will also affect the droplet size. What do you think?
Opponent, please try not to show anything or anything looks like data, okay?
Okay.
Your main information should be provided by the reporter. So you can draw, but don't show something like that.
Yeah, so so back to my question. Did you consider the momentum of the flow rate downward as in the, should be also considered in the experiment?
Like initial state is that going downward, going downward, and like what happened momentum for it?
Yeah, so flow rate I think can be ignored for higher flow rates, and did you really describe that? Because I think including will better incorporate the model to fit the phenomenon.
Yeah, I think that will be considered in the part, like for the whole process is already downward only. That will be taken consideration in the acceleration part.
So did you use this to calculate the results and predict your?
No, we don't have exact value because we want to calculate the exact value, like theoretical value. We have to integrate the value of the fluid, and it's really hard for us to really do the integration. So we did not have exact theoretical data to do the comparison, but we use this to check whether we have the convection.
Okay. Okay. So yeah. So you didn't calculate the quantitative part of the experiment. Now, let me next talk about how you control the flow rate, the experiment.
So what do you mean by exactly by control the flow rates? Like, I get my...
For the entire duration of the dripping, you must keep the flow rate constant, so the dripping pattern will be the same, right?
Yeah, so you're talking about the difference between instantaneous flow rates and average flow rate, right?
No, I'm talking about,
like,
it's okay.
I know what you mean by that. Like, let me show you. I have a discussion of that one. So it's like this one. So as we conduct our experiment, we have a low amount of 10 liters of water, and when a really high flow rate will consume up to 6 milliliters of the water. So making the error between average flow rate and instantaneous flow rate is 0.6%. So that
you mentioned that this is a chaotic phenomenon, so it is dependent on initial conditions, right?
Yeah. So as you can see, the arrow is like real small, so we did neglect it in our experiments.
Okay, so you didn't affect that the fluid will, the small change in flow rate might cause the difference in the dripping pattern, but you still like ignore it.
Since we consider it as a minor impact.
Okay, and my next question will be assumptions of the model, like
assumption model, which page is exactly or something.
Actually, can you just like describe why you should include the bifurcation diagram and
bifurcation diagram just help us to we want to know the linear system, non-linear system, and so specifically in the linear system we also have periodic phase and double phase and chaotic phase, and in linear system we will only have periodic phase.
We know, so this is like only a qualitative comparison of the experiment. Okay.
Yeah.
And next, can you describe what if we change the surface tension of the water? Because you mentioned that the ink kind of modifies the surface tension, and how do you think that will impact the dripping pattern compared to regular water? Because it is mentioned in the proper statement that
surface tension.
No, I mean like the viscosity and the property of the like. Does adding ink change your conditions for the experiment so that it no longer matches the expectations of the problem statement?
You mean like changing the viscosity?
Yeah.
And as I stated earlier, that my viscosity is a constant because I use pure water during the whole my experiment. So those data are using pure water, so the viscosity is a constant. Like and like so the green thing you see in the video is only for demonstrating for better understanding of the motion of the water.
So you didn't really account for yeah. So for the flow rate control, back to the theory, yeah. So you only give it like to give the distinction between linear and non-linear system for the linear stuff. But I think there could be a better model that could incorporate the dripping phenomenon. May I show it to you? Yeah. So may I give a suggestion? Yeah. So say that the fluid is F, right? This is equal to dmv divided by dt, and we can expand this to say dm divided by dt times v plus dv divided by dt times m, right?
Yeah, I believe so, but it is not included in my presentation. So I suggest that we focus on discussing how what is presented in my presentation.
No, I'm just giving a suggestion, like how your theory can be improved using like this
Yeah,
model.
probably could be improved, but I cannot tell you the exact answer there because I haven't tried it like myself. So yeah.
Okay, fine. Then we can move on. And I want to clarify what are some other assumptions of your theory.
Assumption of
Yeah.
theory, like some prerequisite or something.
Because if you didn't really define it, then we don't know if your theory can really determine the dripping pattern of the dripping pattern, or you didn't really have a lot of theory to describe it and only do experiments.
So assumption about it. So I believe the assumption is talking about like it's like this one like both the condition become one and how the force acted on it.
Okay, fine. Okay, so back to the experimental setup.
This one.
I think because most of the experiments is based on the fact that the flow rate doesn't really change that much.
Yep.
So do you think there's a better way to modify the setup so that the flow rate is to make sure like for future experiments then it will be more accurate?
Yeah, we should find a way that we can control. We can minimize the error between instantaneous flow rate and average flow rate. So maybe you can do further discovery on this one.
No, I'm saying that the average flow rate kind of changes with time, right?
Yeah,
because the water level is going down. And how can you improve your experimental model to like better like suit the phenomenon so that the flow rate is really constant?
So you're asking about my future experiment on this one. How can I improve it in my future experiment or something?
Yeah, I'm just saying that.
Yeah, maybe we can reduce the current experience so the error will be smaller. That's when the time experience is reduced. So I think the error will be.
What if the flow rate is going down, right? The flow of water is going down. What if we add another flow of water that's going into the so that there is the same hydrostatic, and therefore the dripping pattern can be like better maintained. What do you think of this setup?
Adding water from that part?
No, adding water from the top part, so that the water level stays constant and the flow rate can be constant as well.
Well, we might consider it into our future experimental work navigation on this one.
Okay. And can you explain, like going back to the bifurcation diagram?
This one.
Can you explain why, for example, in the 0.01, when the x-axis is equal to 0.01, there's like a bifurcation pattern, but then it bifurcates back to like the stable flow rate. Can you explain this phenomenon?
Sure. So based on the linearity, so in the linear system, when you have a small perturbation, it could enlarge or it could be like let me show you this real quick too. So in linear system, it's satisfying the homogeneity. So as when you have small perturbation, it will be in the same degree as the effect. But in the linear system, the effect of the perturbation could be larger, could be the same, or could be smaller.
Yes,
so that could bring
but
about
this is the linear system, right? So in your experiment, you said that the linear system is only the flow rate part. But on the diagram, we can see that the bifurcation part is in the chaotic part. And so this doesn't really fit. I'm asking like, there's a bifurcation process in chaotic, right? Yeah. And going back to periodic, why does this happen?
So as I say, the perturbation might be increased at the same degree, or bigger degree, or smaller degree in the nonlinear system. So that could happen, the periodic phase could happen in the nonlinear system.
Well, what if changing the flow rate actually changes the trajectory of the possible path in phase?
Time is up. So, Paula, you have 1 minute to summarize the discussion, please.
Okay, so first we clarified the experimental setup that they should have add another thing to the water to make the water level constant. And that is the experimental setup. And then I kind of clarified about that their equations only describe the qualitative part, and it is the part where the distinction between stable linear system and more chaotic non-linear system, but it doesn't really describe the flow, which kind of contradicts with the following statements and asks us to explain the phenomenon. In addition, I also asked about the different assumptions, but he didn't give me a clear answer on that. And also asked about whether the ink from the surface tension from the ink affects the water, because in the first definition we should use water and not like ink. But he also didn't give me a fair answer on that, so he only mentions that it can be affected. And we also talked about the nonlinear part of the system and how it might have this phenomenon that is going back to the linear part.
Okay, I would like reporter, please also get down to the stage, and opponent, please on the stage to answer the question from the reviewer.
Okay, I'm the reviewer. Good morning. I have some questions for you. First, for both of you, what is the key parameter in a review?
Well, of course, it's the fluid properties and flow rate.
Parameter is key parameter. I've been working for it. That's all my experience on the balance.
Okay, so can you mention possible errors in your experiment? Because I don't.
One of the possible errors that I discovered earlier is that the difference, the error between instantaneous flow rate and average flow rate. And we do consider the error is between like 0.26.
Okay, thank you. So can you turn to page number 22?
Okay, sir.
So are there any errors in this group?
Like I calculated the error afterwards, so we didn't really put a correction on it. So we just tell how error is caused, but we do not have to correct.
So the scattered spot on the right, how do you know it's caused by chaotic or it's caused by error?
Well, if you look closely, it wouldn't be like so small bucket feeding. So it will be a one-time feeding, so that we can ensure that it's not only caused by the error. So.
Oh, okay. And this for the opponent. You just asked the reporter about the fabrication diagram. So what's your opinion on that?
So I actually tried to say it in the end, but anyway, I think that it slowly progressed from periodic to period doubling to chaos, and then back to period doubling and back to periodic. I think in their diagram, and I think this is due to the fact that when the flow rate increases, the trajectory of the motion in phase space is actually different.
Okay, thank you. So can you turn to the experiment setup? Next one. Yes. And you can see that the picture in the middle, the radius isn't always the same.
Oh wow! So basically, as the flow rate is going downward, so we consider the flow rate as distinguished one because it is the terminal outcome of the water.
Okay. So about the opponent, do you think this setup will affect the result?
Well, I think it's part of the result. Like this, if we're asked to describe the drop interval, then we need to look into drop shape. The fluid dynamics is influenced in that, and the droplet rate and the pulsar radius is also an important part of this.
Okay, so we do control temperature change in
So in our lab, like temperature is controlled. We have a thermometer on the wall, so it is controlled.
On this control.
Okay, now is the preparation time for reviewer. Okay, preparation time is up. Opponent, please take on your stage. 4 minutes.
Okay, I'm going to review the carbon number 6 turbine forces. The main forces are turbine patterns and time different drops. And this is a summary of the recorder. The theory that is in the presentation is chaotic system, non-stroke equation, shape of the droplet and motion of the droplet, stroke tension, velocity, and damping of the liquid. And your experiment setup is consists of high-speed camera, full-set tube, pocket, and electronic scale. And the parameter is flow rate to time interval patterns of droplet. And overview of the recorder, and the pro are they have enough explanation on theory and clear demonstration videos and taking explanation on the phenomenon and also comparison of participation diagram. But there are still some cons. The first is they lack error analysis, and there are not enough data to show chaotic system, and there are clear label on the data graph, and last, they didn't have deep observation in the shape of it. And overview of opponents. The first is that the nation force analysis and good time management highlight the importance of high flow rate and a deeper understanding of force analysis. The cons is not, they didn't fully understand the presentation, and they didn't discuss according to the recorded presentation. And this is the missing points in the discussion. First, the error analysis and definition of theory model and also critical conditions. And this is the discussion. First, the opponent asks how to control flow rate, and the reporter answer is they calculate through the experiment. And our opinion is that we partially agree with the reporter seeing the flow rate cannot be easily controlled. And taking the opponent asks force diagram before droplet drops, and the reporter answers the surface tension and gravity. And our opinion is velocity is also important, so the recorder should consider that. And the last, the opponent asks what will happen if the surface tension is deeper. And the recorder answers that they didn't do it in the experiment. And our opinion is that they should consider it. And the opponent asks that nonlinear and linear interpretation diagram, and the recorder answers the definition of it. Our question is error analyzed in the graph of experiment. And our opinion is that the recorder should be more clear on the error in data. And also the calculation diagram, and our opinion is that the chaos phenomenon is also important. So, and our question is the key parameter, and the opinion agree with them. And the recorder answer flow rate, and the opponent answer flow rate. And radius of full set, the recorder answer achieves the most secure one, and the opponent's rate is an improvement parameter. Okay, this is the presentation.
Okay, so next will be the concluding remark for the reported figures.
So thanks host, opponent, and reviewer. So there is also some points that I want to clarify. So first on the theory part, so for the sake of why we use linear substitution is that it assists us in determining whether the convection exists or not. And about the duration of the oscillation could be the same, could be as the same degree, or even larger, or even smaller, causing the appearance of the periodic phase or double-deck or chaotic in the linear system, because the opponent doesn't really understand what I'm saying. So basically, you want to know why there's a periodic phase in the nonlinear system. So this is the main cause of why. So the oscillation could be in the same degree. So that is why there will be periodic phase in the nonlinear system. And about our experiment and data analysis. So the first breaks that the viscosity is not a constant throughout my experience, but I think I stated twice that I use pure water throughout all my experience. So experiments, so our viscosity is under control. And the error of the average flow rate compared to its instantaneous flow rate is like up to 0.6%, so it could be smaller. So, which is rather reasonable for us to neglect in our data analysis. And since that instantaneous flow rate varies every moment, so the opponent's suggestion by adding water in the budget to maintain hydrostatic pressure is practical to us. And the driven interval is considered in our experiment here, and I don't really know why the opponent stated that we didn't consider driven interval. So in the experiment here, we did discuss how water flow rate affects the driven interval. And this is my concluding remark. Thanks for your attention.
Okay, I would like to ask all three presenters to stay on the stage and ready to answer the question from the jurors. So any question? Please.
What's the key parameter of the experiment?
Key parameter
of this part.
This page or this experiment?
Before
the water forms.
Okay. Why I see the size of the water drop be the key parameter? Have you ever measured the size of the water drop? Will that be the same all the time, or it will change with the circumstances? The opponent.
Do you mean that the size of the water?
Water drop.
Water, okay. So, yeah, of course it might affect, because for higher flow rates, the droplet size might go.
Let's make it simpler. Can you propose a method to measure water drop, the size of the drop, or the mass of the water drop?
Oh, okay, I can provide an explanation. May I use the...
I don't need an explanation. I need you to propose a method to measure the water drop, the size of water drops, or the mass of the water drop.
So I would use, first, of course, I use the camera to take a photo. Then I would use tracker to get the radius.
I think that's already enough.
So for me, I said earlier, so I just...
You need any answer from him?
Yes, I need, because...
Okay, please answer.
Oh yeah, so I captured the instant before dropping, so that is when the full droplet is formed, so I
propose the diagram.
Oh yeah, sorry, that's my mistake.
Any other question? Yeah, please. This is microphone.
So for the last part for the chaotic phenomenon, I would like to ask the reporter and then the opponent, what is the key parameter to have this chaotic phenomenon? Is it related to some kind of intrinsic property of the water or the damping oscillation? Yeah, because at the beginning you have said something about the damping oscillation, and I think it's some kind of dynamic phenomenon, and you cannot decide what phase. Yeah, because usually for an oscillation, the phase is very important. Yeah,
so about how I define the chaotic phase is that when the oscillation is not yet reached equilibrium, so it will bring about the chaotic phase, because when droplets are already about to fall in, but the oscillation is still remaining, so it will affect the pattern and the interval of the droplets. So now they are stated as the chaotic phase. So the oscillation is the main factor of acceleration in chaotic phase.
Yeah, I also think it's the damping oscillation.
Any question? Please.
Reporter, I think you did measure the relaxation time or the damping oscillation returns to equilibrium. You do use high-speed camera to analyze it, right?
Yeah.
And what's that rate compared with the drifting rate? It is comparable when the nonlinearity occurs. Is that correct?
Discuss it.
That is the drop. dripping rates, one of those time, and also this relaxation time back to equilibrium. This is comparable. When this is comparable, then you observe the, say, chaotic or non-linear behavior. Is that the
yeah, so I get the dripping rates and the limiting oscillation rate. Yes, and compare this, then I further know whether it is chaotic or not. So
you didn't do that part. Did you reach the chaotic stage?
No.
No, okay.
Okay, so if there's no further questions, so we move on to the scoring part. Okay, I think looks like all the scores are even. So please raise your score for the reporters. So the scores are 8, 6, 7, 8, 7, 6, 8, 5, 6, and 6. The score for the opponent. They are 7, 6, 7, 7, 7, 7, 8, 7, 6, 6, 8. And in the last, the score for the reviewer, they are 7, 5, 5, 6, 8, 7, 7, 8, 6, 5, 7. Okay, for the reporter, we have the low mark for 5 and several 6 and 7 and the high mark for 8. So can you give some comments about 5? I think that's, yeah, please.
I think the reporter mentioned that this Stokes equation. It can have chaotic system, but not it's a general. But you have to specify how you should, in this case, why, what parameters are important. That's what I think is important. So it doesn't have any theory. Except the some reference application, saying the application that doesn't solve that. Stokes theorem application. Stokes equation is a partial differential equation. You have boundary condition, etc. Quite complicated. It's not something that you should just present. You just say this one.
Any comments from the high schoolers? No. Okay. Okay, I personally have some comments. I think that your work, the problem say parameter affects the phenomena. Okay, but looks like you described the phenomena only. You didn't control any relevant parameter, even not finding it. Okay, I think that's a big deal. Okay, for the opponent, the score is quite even, from 6 to 8, and mainly focused on 7. So any comments from any one of the jurors? No? Okay, that's okay. I think it's okay. Myself, as some comments, is that the opponent, you try to raise some problem, try to raise some discussion, but looks like you are failing to find out the discussion point to the problem. The problem says find out the relevant parameter, but you focus on some superficial parts they present, but you didn't point out to the problem itself. Okay, so I think that's a little bit different. And then for the opponent, we have 2-5, 1-2-6, 3-5, 2-6, several 7, and 2-8. So for the high mark, any comments? And then we ask for the low mark. No? So for the low mark, for the 5.
Okay, sorry, for the low mark. Yes, one reason is that at the beginning you asked a general question. I mean, you are asking what's the critical parameter or something. That I cannot feel that you are trying to target something. You are just asking a general question. You just want some answer from the presenters. And another big disadvantage is that you are presenting facing the screen, not facing to the audience in the overall presentation. That's a big pity, I would say. Yeah. So.
Okay. I think that will be all. I would like to close this round and take 10 minutes break. So please come back in 10 minutes. The clock now is 10:50. So please come back at 11.
不想回去。还是我们就晚一点，大家做 Spider 实验。还是我们就晚一点，然后大家做点力比较大。上次就是这样啊，我们就放比较
没有人。我在看猫猫，你看看。我以为他跟我朋友看猫猫。我来要钱好不好？不行，我也要。这样我要帮我家拿出来。那我哪一些？对啊，他就是够球。哦，这样。 去看一下我传的。OK。
哦，好，我也看，我也看得到，可以靠这个拍。我看你跟林迪吵架。
因为你那时候他是，没有，你一开始是说他只会弄那个。
没有，他是
你是这样子。
然后他就是说，
你想这个有这个。
在哪里啊？教育。更高一点。哦，我看到那个。这回头，他你的他，给他高分，然后中间送。
Okay, it's about time. So please all teams prepare for the last round. Okay, it's about time, so I would like, so all three teams are okay. Okay, I think we can start the third round. For the third round, the reporter will be Lagrange's. Opponent is Andy Joker, and the reviewer is Ningdao Mei. Okay, and the problem to be discussed will be number 3, Lato. And now is the time, 5 minutes preparation time for reporter. And you can start whenever you feel ready. And also, during the preparation time, all 3 teams, please put down your presenter's name on the board. Okay, please start your presentation.
Okay, so good morning, dear viewers and readers. I am the reporter from the Lagrange team, Andrew Lee, and today I'm going to report on problem number 3, Lato. And so first, let's start with the introduction. So first, let's take a look at a problem statement. If we attach a ball to end of a string and connect the center to a pivot, and if the pivot oscillates along the vertical direction, the balls will start to collide and oscillate with an increasing amplitude. Investigate this phenomenon. So we think that the key questions here will be the effect of the collision in this phenomenon, as how the statement has stated, and the relevance between the frequency of the oscillation of the pivot and its amplitude. So this is our observation video. So first, we would like to clearly define the amplitude. We define the amplitude as the pendulum, as the maximum angular displacement. And the key units we will use here is the radians. So first, let's start with our theory. So first, we assume that the motion of the pivot can be estimated as a sinusoidal wave. For this, through differentiation, we can get the acceleration of the pivot. And thus, we can calculate the acceleration of the ball through calculating the pendulum equations. And substituting in the pendulum's natural frequency, we can get the motion of the equation like this, assuming the conservation of the momentum. So this has no consideration of the damping. However, in real-world conditions, there will be an elastic collision causing the damping and energy loss. So we need to factor the damping of the collision and the spring. So we will add the damping factor right here. And we assume the symmetry. We will take the absolute damping factor in the ball side. So you will substitute this equation like this, and the equation will switch sides every collision. So this is a nonlinear differential equation. So we will solve with a Python numerical solution. For intuitive explanations here, because of the absolute value right here, the frequency will get multiplied by 2. This means under resonance conditions, it will be the 2 times the original pendulum's natural frequency. So let me show you the numerical solution. So here, as you can see, as the pivot is oscillating with 2 times the pendulum's natural frequency, the amplitude will reach a maximum. And as you can see from this graph, the angular velocity is constantly increasing with an exponential. And as you can see from the phase-space diagram, the amplitude is constantly increasing as well. So to give a more understanding on the trajectories of the lato-lato, we plot the phase-space diagram. So from this phase space, we can see that there is a stable oscillation right here. And the red right here is the collision phase. Well, for this, we can calculate the highest amplitude. So we can define this as a nonlinear chaotic system. And if the opponent would like to talk more about it, I would be happy to elaborate it in the discussion. So first, we want to calculate the damping coefficients. So this is the original equation of motion. And without pivot oscillation, we can calculate the damping ratio throughout the experiment via substituting the matrix equation into this equation. So if we assume that collision is the main factor causing the damping, we can use an energy equation to get the relation between the coefficient of restitution and the damping ratio. So this is a theoretical relation. And this is the data analysis, which will fit the curve and get the damping ratio as 0.0245. However, the theoretical results calculated by the collision coefficient of restitution is 0.01. So we can get that the theoretical values are lower than the actual values. So this means that collision is not the whole picture of the lato-lato. And calculating damping ratios can better account for the other energy losses like the string stack and energy dissipation. So first, we will start with our experiments of the pivot frequency. This is our experimental setup. We use a Lego machine here for an oscillation, and we test it on different frequencies with the 2 same balls and the same string length of 20 centimeters. And from here, we can get that the y's amplitude is 3 centimeters, and the x amplitude, maximum amplitude is about 0.05 centimeters. So it has a magnitude smaller than 5%. And this is our experimental videos. As you can see right here, when the frequency is closer to resonance, the amplitude will get larger. So this is the analysis. So we have done the theta to t graphs of the different frequencies. Okay, so from this graph of the angular velocity, we can see that there is a pure collision happening at the high speed. And this is the result of the 2.42 Hertz and the 2.1 Hertz. And as you can see, the natural frequency is about 1.9 Hertz. Resonance frequency is about 1.9 Hertz. So this is the closest frequency that we get to to the resonance frequency. And we can get that this amplitude is very large. However, at large amplitudes, the motion of the lato-lato will become very unstable, as we can see from this angular velocity. So we have plot the stable states of the phase space under far from resonance conditions. And as we can see, as we approach to the resonance conditions, the amplitude will get larger. While stretching is a fundamental characteristic of chaos, which I will elaborate more if the opponent wants in the discussion. So we will talk about the resonance phase, where the phase space is a little messy. So as you can see right here in the phase space, this phase space is pretty unstable with a very high amplitude. Okay, so I would like to do a Fourier transform. And you might be wondering here why the theory's Fourier transform is different from the experiment. So in the theory, we can see that there is a pendulum frequency and a pivot frequency. While in the experiment, only the pivot's frequency exists, and the pendulum's frequency is non-existent. Well, the same phenomenon can be observed in the 2.67 Hz. And we can get that there is also a pivot frequency and a pendulum frequency. However, in the experimental results, the pendulum's frequency is almost non-existent, as we have mentioned earlier. So, back to this Fourier graph, we can get that these frequencies are pretty close to each other with octave frequencies. So this will cause the beat. So this is why the amplitude will increase, as the problem statement I mentioned. However, due to the beat, it will also decrease as well. While the beat and the different frequencies demonstrates the non-linearity of the system. So we have a hypothesis of why the pendulum frequency is non-existent in our experiments. So our hypothesis is the synchronization. Due to the string stack right here, the effective length of the string will be smaller than the actual length of the string. So if we calculate the effective frequency, then it will get a little bit larger. So the resonance frequency can be modified to a larger extent. So this is why at larger frequencies, the synchronization may happen. So we do a verification with the 3.168 Hz and with a stable phase space. Okay, so we can get the frequency. The main frequency is 3.168 Hz, which is same as the pivot frequency. Well, here, there is no other closer frequencies due to this system being more linear than the non-linear system. And as you can see from the pictures right here, we have at the highest point of the pivot, you will have a collision. And at the lowest point of the pivot, you will have a large angle. So meaning a complete synchronization. So we do a comparison of the amplitude with the theory and the experiment. So according to what I said earlier, at close to the resonance conditions, the string stack will cause a decrease in energy as the amplitude gets very big. While at the far from the resonance conditions, synchronization will increase the amplitude. And this phase is the phase where the damping energy is smaller than the conserved energy input. So this is the logic. The previous frequency is same as the false oscillating frequency under the conditions of the stable state. But if the amplitude increases when close to the resonance frequency, it will happen at the 2 times of the natural frequency. And the stable state will occur due to string stack, causing synchronization. And that is why the pendulum frequency is non-existent. And beat occurs due to the non-linear effects of the motion causing octave frequency. And next is the experiments on the string length versus the amplitude. So this is our experimental setup. We use 4 different string lengths with 20 centimeters, 30 centimeters, 40 centimeters, and 50 centimeters. And this is our hypothesis. So according to our equation of motion, with a small angle approximation, the acceleration will be proportional to the L to the power of -1. So if the L is bigger, then the amplitude should be smaller. Also, another effect is that when the L increases, there will also be more damping as the string has more chances of energy dissipation. And this is our experimental videos. And as you can see right here, as the length increases, the amplitude will have a sharp decrease. And this is our results of the theory and the experiment. And as you can see right here, you might be wondering that why there is a different distribution between these 2 theories, between the same theory. Well, I'll explain that later. So, the first discussion is the distribution that we can plot as a Gaussian distribution. Well, this happens when the maximum amplitude is smaller than 90 degrees. So we can make the Gaussian curve to get the middle point resonance frequency. And we find that the experimental resonance frequency is larger than the actual resonance frequency, indicating the string stack is existent and the synchronization is here. And the same phenomenon can be observed in the 50 centimeters. Well, this cell-like distribution shape right here happens when the maximum amplitude is bigger than 90 degrees. And it will exhibit the phenomenon that I have shown earlier. So this is the theoretical explanation. At the amplitude smaller than 90 degrees, the force can be modeled as assigned right here. So it will be more stable for Gaussian fit. However, when it is bigger than 90 degrees, the distribution will differ due to increased denominator effects. And this is the nodule. The amplitude increases when close to resonance frequency, and the amplitude decreases as the length decreases. And we have two cases, bigger than 90 degrees and smaller than 90 degrees. And this is the conclusion. Now, we can answer the key questions from the problem statement. The first question is the effect of the collision in this phenomenon. The collision can be considered as damping in the pendulum system, and the collision will contribute to the Gauss switch, assuming the symmetry, making the resonance frequency 2 times the natural frequency. And next question is the relevance between the frequency of the pivot and the amplitude. The ball oscillates at high amplitudes when the pivot frequency is close to the resonance frequency due to energy conservation. And the amplitude is lower at longer string lengths, and the resonance frequency is also lower with a smaller natural frequency. Thank you.
Okay. Following the time for the opponent to ask questions for 2 minutes.
Okay, thank you for your report, and this is the opponent. I'm going to ask you a few quick questions. So first, you talk about the damping coefficient. I want to ask if you consider the energy loss due to this lack of string in the
the damping is calculated via the experiment, so it considers both the air resistance, the string stack, and the collision in acid collision.
Okay, so every factors of energy loss is considered into the coefficient.
Yes, because it's measured by the experiment.
Okay, good. And how about page 9? So in page 9 you talk about chaotic phenomena.
Yes.
And did you actually see this in your experiment result?
Well, yes, I have plotted the base in my appendix. I think that they can be set for the discussion.
Okay, then we'll talk about it later. And what about your errors? Like, did you calculate an actual value of error for your experiment data?
As you can see from the plot right here, we have the errors right here from the theory and the experiment. Right here, and we can basically, I think you can see from the graph. Yes, and I have calculated, but I didn't have the actual numbers in my phone.
Okay, and okay, I get it. And I think this is all my quick questions. Thank you.
Okay, thank you.
Okay, the preparation time for opponent is 3 minutes. Okay, that's all the time. Norton, please take on stage.
Okay, hello everyone, this is Peter from the Geographic Missouri, and today I'm going to talk about problem number 3, Lato. And this is the problem statement. Attach a bond to each end of the street and connect the center of the street to a pivot. When the pivot oscillates along the vertical direction, the poles start to collide and oscillate with increasing amplitude. Investigate this phenomenon. And the main focus of the report is the effect of collision on this phenomenon, and also the frequency of the pivot amplitude. And this is the overall summary of the report. So in the theory, they assume that the motion of the pivot can be described using a sinusoidal wave. And they also consider the energy loss by calculating the damping ratio according to the experiment they have. And they also talk about the stable oscillation, which is when the synchronization happens, and also about nonlinear and chaotic situations. And they said I didn't really think he described detailed in the setup, but it is obvious that they show a picture of the experiment. And the parameters, they change different frequency of the pivot and also different screen depth. And their conclusion is that in the stable state, the pivot frequency is, the pivot frequency and collision frequency are very similar to the resonance frequency, which is synchronization in a stable state. And the amplitude will increase when the natural frequency is close to the resonance frequency. And this is the overall advantages and our suggestions for the report. So I think that what they did very good about this whole problem is that they have a very detailed discussion both in the experiment data and the theory. And they also have a very clear graphical demonstration of either their experiment and also their data. And they also have a lot of comparison between the key parameters, which is the length of the string and also the frequency of the pivot. And our suggestion is that we think that they should show more quantitative error analysis, such as calculating the actual energy loss by not only by using their experiment data, and also we would like to talk more about the definitions and the conditions of chaotic system, and also if they did any error correction in their experiment. And these will be my points of discussion. So I would like to invite the reporter to discuss it.
Okay, please start the discussion.
Okay, then can you please turn to page 9 of the report?
Page 9?
Page 9, yes.
Okay, so you mean the phase space diagram? Right?
Yes, can you explain more about this diagram? Because you said it a little bit quick, I didn't get a lot of understanding on this diagram.
Okay, so the phase space vector is the positive. Okay, so the phase space vector basically plots the trajectory of the movement of the lato. So, like there are two balls, right? So there are the left ball and the right ball right here. And the phase space here is, this is the omega, and this is the beta. So at this beta condition, they will have like an omega right here. So it will like have a decrease and go from there to here. So it basically gives us more of an understanding on how the trajectory is happening when the lato is in.
So what you're trying to say in this diagram is that for a certain value of theta,
yes, there will be like
omega.
Yes.
And this is why you think it can be explained as chaotic.
It can be explained as chaotic because we can talk in that phenomenon moments, which I can show you in the appendix. Okay, sorry. So this is our appendix, which we have. So we have a 6-dimensional phase space because we have the two balls, right? And we have the phase space of the pivot. So this is 6-dimensional. We can calculate the initial separation and get the Lyapunov exponent through mathematical calculations. And we can calculate the Lyapunov exponent as positive. So here, this is because that there is a constant energy input caused by the pivot, and the damping is smaller than the conserved energy input when at close to resonance spaces.
Okay, so then what about the chaotic, like, what causes it to become a chaotic system?
Okay, so I'm very glad you asked. And may I use the backpack? Okay, so. Okay, so from my report, I said that there is a resonance frequency, right?
Yes.
Okay, so you can understand this. That, so you know that the resonance frequency, the energy here is a constant, and here is a fluctuating energy input caused by the pivot. Yes. So at the resonance, the energy is the most constant. So you will like have a high energy, and because there is the energy input, it can maintain the chaotic state. And we have also calculated with a Lyapunov exponent that is bigger than 0, we can think that this system is sensitive to initial conditions. Also deterministic according to our theory. And this is non-linear with an infinite timeline if we assume that the sinusoidal wave has infinite timelines.
Yes, I want to ask, why do you think that this is sensitive to initial conditions? Can you explain more on how it is sensitive to initial conditions?
Well, basically, if you calculate the Lyapunov exponent, so the Lyapunov exponent is basically if you have the two nearest points in the same phase space. Right. And if there is like a time duration, there will be a new distance, right, with the t. So basically, the Lyapunov exponent calculates is the logarithm of these distances throughout the time. And if we calculate this slope, we can get that if the distance is increasing or decreasing. And it is increasing with a big slope, then with the big slope greater than 0, then we can say that this system is sensitive to initial conditions.
Okay, so back to the more basic theoretical explanations. Do you agree that when it is close to the resonance frequency, the energy loss can be balanced out? Like it is the most balanced out of energy loss.
Okay, so according to
because like in this phenomenon, the lado, the string will do work on the two balls, right?
Yes.
Then do you think you agree that my explanation on if the work done on the two balls can balance out the energy loss, it will have an equal amplitude or maybe an increasing amplitude? Do you agree with this explanation?
Oh, actually, I disagree. So if it has a resonance frequency, right? So you will have like a large amplitude. So the large amplitude right here will actually increase the string stack and increase the energy loss. So as you can see from my graph right here. Okay, so as you can see from my graph right here, like when it's close to resonance, like it has the sharpest drop, right? So it means that the energy loss is the highest due to a big amplitude having a more string stack, right?
So for a higher amplitude, there will be more energy loss.
Yes.
Due to the string stack.
Due to the string stack.
Then if there's more energy loss for higher amplitude, why would it be? How does the amplitude be higher if it has more energy loss?
Because the conserved energy is different. It's because under resonance conditions, more energy will be conserved in the system. Not all the energy of the pivot will be conveyed into the loss.
Okay, so are you saying that for a higher amplitude, the energy loss will be bigger?
Yes, but however, its total energy input into the system is bigger than the other non-resonance conditions. So the net amplitude will be bigger. This is what I explained.
Okay, so the energy input will still be bigger than the energy loss, even if the energy loss is bigger.
Oh yes, so that is why there is the amplitude.
Okay, I get it. And also, let's stay at this page. So the graph for 20 centimeters,
yes.
Like at the peak over there, why is there a fluctuation here? Why?
Well, I think this is due to the non-linearity of the system, and I have explained in my my slides that when it is bigger than 90 degrees, it is the non-linear of the system will reduce.
Then, if it is due to the non-linearity, then why did the other two graphs show the same trend?
What two graphs?
Like for 30.
Well, okay, so at the 30 centimeters right here, you can see that there is the same phenomenon, however, it's smaller. Well, this is because at 30 centimeters, like the energy is lower, right? So the energy insertion into the chaotic system will be lower. So so this will happen that the phenomenon.
Yeah. So you think that this difference in 20 centimeters is due to the chaotic.
Yes, it is due to that this is a non-linear system.
Yeah. Okay. So my suggestion is that since it is, you mentioned that it is due to the chaotic phenomenon, then
yes.
Since the chaotic phenomenon is highly sensitive to initial conditions,
yes.
so I think that maybe you can try to do more experiments on maybe closer temperatures, such as 21 to 23, and maybe you can find like.
Oh yes, yes, we can definitely do more experiments on that.
Yes, I think that's a way to show more clearly that it is due to the chaotic system. Okay, then next I want to talk about the error of these data, because since you explained that all of the energy loss, like the factors of energy loss is considered into the density ratio, which is calculated at the top right of the diagram. Is that correct?
Yes.
Yes, so then since you calculated the density ratio, did you try to calculate the actual value of energy loss and try to prove that this is why it causes a deviation in your experiment?
I mean, the theory already has accounted for the density ratio. Yes,
yeah,
and energy loss is mostly due to the other effects of the string stack in the difference in the effectiveness of the string causing the synchronization.
Oh, so you.
And,
okay, so the damping coefficient is calculated from the.
It's calculated from experiments because we do.
From the deviation between experiments.
No, we do separate experiments on where the pivot is not oscillating, and we have like the lapo right here, and we plot the T graphs, and we fit exponential curve.
So it's so you fit the exponential curve, and then you
yes, we do separate experiments to calculate the density ratio.
And then you compare it to the series.
Yes, and we substitute we do another experiment to calculate the density ratio. We substitute the results from that experiment of the density ratio into the numerical results of my nonlinear equation.
Okay, then how do you know? How did you calculate the damping coefficient without knowing what the actual loss of energy is?
I think you.
Or maybe I have to say it in another way. Can you know the exact value of energy loss? Because since you have a theory to predict the energy, and then you do your experiment and see that it's different from a theory, then can you calculate the actual energy loss?
Oh yes, of course I can calculate the energy loss. But I think the policymaker here has mentioned the entropy, so that is why that is not in my slide. However, if I am investigating the whole phenomenon, I may do more slides on the energy calculations.
Yes, so and then the density ratio is.
First, I think you misunderstood how we calculate the density ratio. Okay, so this is a slide which we calculate the actual density ratio and the theoretical density ratio caused by the coefficient of resolution. Okay, so the actual density ratio is done through a separate experiment with no pivot oscillation, and we fit an exponential curve to get these ratios right here. Yes, so it already accounts for the natural effects of the string and other things. However, it does not affect for the string stack when the amplitude is increasing.
Yes, so I think that maybe there might be.
Yes. So maybe yes. So maybe that if the string stack can be considered, then if the nonlinear will.
Yes, so I suggest that maybe you can, since you know the theoretical line and also you did your experiment, you can calculate in actual how much the energy loss is, and then you also have the damping ratio, and you can calculate it. And since you didn't consider,
and we can find the difference between the damping ratio from the other experiments
yes, and then you
and
can
the results from the last one.
Yes.
So I know
this is my discussion.
Thank you.
Okay, so please deliver your summary of discussion.
Okay, this is a summary of discussion about the opponent. So in the theory part of the report, we discussed about the definitions of chaotic system and what causes the phenomenon of chaotic. And we all agree that it's sensitive to initial conditions, and agree that they should do more values of closer values of their independent variables to show it is sensitive to initial condition. And also the next main part we discussed about is energy loss, and we clarified the way of calculating the damping ratio. And then we also agreed that since they have an experiment value and a theoretical value, they can calculate the actual energy loss. And since they didn't consider stacking of the spring into the damping ratio by calculating the energy loss from the damping ratio and then trying to find the difference between it and the actual value of energy loss. They can actually get a more accurate showcase. Thank you.
Thank you. So please pause. I'm ready to answer questions from the reviewer. Please.
First of all, since you guys have mentioned the damping coefficient, and the reporter says that the deviation before the theoretical data and the experimental data is because of other factors, then I would like to ask the reporter, what's the damping, like what components is included in your damping theory, and what's the other factor that you have not considered?
Well, I think that you misunderstood my point. My damping coefficients are all calculated via the experiments without the Piquet oscillation. And the deviations will be quantified under the Piquet oscillations. There will be different effective string names, and there will be like different energy conserved and different energy loss. So I think that is my point.
Okay, so also a question to the reporter. So when you mentioned the conclusion, you mentioned the relation between the amplitude and the length. So I would like to ask, when you say the amplitude, do you mean the maximum amplitude?
Yes,
or
I'll clarify that. Here we use the maximum amplitude, so that is why there are no error bars in the output.
And so also, you observe the phenomena that the lateral swing angle goes above 90 degrees.
Well, under that case, the amplitude will no longer be decreasing, so I don't think that is the problem statement is making about.
Okay, since you guys talk about chaotic situation a lot, I would like to ask both of you guys, what's the basic phenomena that can represent the chaotic in lateral motion?
Sorry, can you rephrase your question?
The physics, like...
you mean the physics behind the
other than from physics.
Okay, so first, so because it has an energy dispersion, right? So the energy dispersion will maintain the chaos state. So that is why there is chaos in the system.
Yeah, just like you talked about in the 4 different graphs, I think that they have to do more closer analysis to show that it is chaotic, and I think that this is something possible to let us see that it is actually chaotic in the physical phenomenon.
So another question for the reporter. So the frequency, the angular frequency equation you're using is for the slowing code, right?
No.
No, since you don't show the correction.
No, we have the sine beta.
Oh,
have a sine beta there. So we use the numerical solution because small information cannot be used in this context of the lambda model.
Okay, so what's your assumption on the pendulum? Like when you your theoretical data, do you have some assumption like the string is always taut or something like that?
Yes, in my theoretical assumption, I have assumed that the string is a rigid body. However, in my experiment results, we cannot see a pendulum frequency, and that is because of the synchronization caused by the effects of the string.
Okay, and then in your experiment, have you measured the coefficient of rest?
Yes, sir.
Oh, okay. That's all my question.
So, your preparation time is 10 minutes. start. So please start your presentation.
Okay, so this is a reviewer from Team Xiaomei, and today I'll be reviewing problem number 3, Lato Lato. And so, with the problem statement, the main focus of the reporters includes the effects of the collision phenomenon. So, this is an overview of the reporter's presentation. So, the phenomena is pretty obvious as the one stated in the problem statement. The two blocks collide and with the increasing amplitude. And in the theory part, they use damping oscillation and equation of motion to describe how bipolar system works. And in the experiment part, they control the pivot frequency and to see the angular velocity. And also, they have string length against the angular velocity as well. And in their conclusion, they stated that when the amplitude increases, the natural frequency is close to the resonance frequency. And also, in stable states, the pivot frequency will equal to the collision frequency. And here's are some pros and cons for the reporter. So in their presentation, I think they have a clear observation on the phenomenon. And also, they have comprehensive comparison between their theory parts and their experiment part. But our suggestions is that they could elaborate more on the graph they're showing to clarify some points. And also, they could have more error correction, like to make some corrections to see if their hypothesis fits their experiment data. And here's a review of the opponent. So in their opposing, I think their pros is that they have effective questioning and they have identification of the experiment faults. But our suggestions for them is that they could focus more on how the theory part works and also the other parameters of the experiment. And here's the summary of the discussion. So the opponent acts at higher amplitude. Why does the amplitude increase even increases even though there's bigger energy loss? And the reporter answers that the conserved energy is different, so that the higher amplitude, the net amplitude still increases. And we agree with the reporter. And the next question is that what is the fluctuation is smaller at 30 degrees rather than 20 degrees. And the reporter answers that since the conserved energy at 30 centimeters is that, which also fits what they have stated in the last questions, that the conserved energy is different in different situations. And we think it's necessary to find also the suggestion for the reporter is that they can find a critical value of how the parameters decrease. Okay, and here's the point split. You think about the reporter and the opponent. So I think they have, in their theory part, they can elaborate more or even show how the phenomena to explain the chaotic situation that I have mentioned. And also the parameters is that the slacking condition causes the deviation is not calculated. And that's the data analysis, they could have more error correction. And this is my presentation. Thank you.
Okay, finally is the concluding remark from the reporter. 2 minutes, please.
Okay, so first I'll thank both the opponent and the reviewer for this amazing discussion, and I'll go on with my concluding remarks. Okay, so this is my remarks. So first, let's talk about the Lato-Lato phenomenon. So the Lato-Lato phenomenon inhibits the non-linear properties according to our equations. And the applied damping ratio is the effect of the energy loss. So we have considered damping behind the experiments without the physics oscillations. And the beat was explained by the increasing and the decreasing amplitude in the phenomenon. And the string stacking will explain effective string length, and the synchronization. Okay, so this is the opponent's interpretation. So they at first asked us about the damping, and we have clarified that our damping has already considered air resistance in elastic collision and some sort of the string stack without the pivot oscillation. But however, I think that if the pivot is oscillating and it has an increasing amplitude, the damping may have some difference. However, this can also be modeled through the extent of the effective string length. And the total energy loss is irrelevant, and because the power statement has only mentioned the amplitude. And the reviewer, we have also clarified with the reviewer that we did not use a small angle approximation, and we used the sine theta to solve for the numerical solutions. And we also have clarified with both the reviewer and the opponent our definition of chaos with the deterministic factors, the nonlinear effects, and a positive diagonal exponent. And we also have clarified how the energy is conserved at the resonance frequency. And that will be my concluding. Thank you.
Okay, thank you. So I would like all three teams to get on the stage and ready to answer the question from jurors. So any questions? Yeah, please.
The question for the question. You mentioned that in your presentation, you say that there's a resonance phenomenon here.
Yes.
Is a resonance similar to ordinary resonance phenomenon? How is it different?
Can you give an example on what you mean by the orderly resonance?
Okay. The simple in the traditional way, the force is applied on the ball.
Yes.
And then it swings and gets resonance.
Yes.
But when you apply this way,
yes,
would that be different?
Well, I think it is the same. And because
It's the same.
it
So
is,
the frequency, resonance frequency is the same.
it is 2 times.
What part?
So the original pendulum's natural frequency, and the resonance frequency of the pivot is 2 times the pendulum's natural frequency.
So in the usual, the resonance frequency is the same as the pendulum.
Well, it has a 2 times relation according to our equations and simulations.
So have you investigated if you go higher frequency, you get the resonance?
It will be when it is far from resonance, it will be like a synchronization, meaning that the.
But I just say that if you change the
oscillating
frequency more and more, you get the resonance.
The amplitude.
Or if you try 4 times, 3 times, etc., you get the resonance.
Yes, we have tried experiments multiple times.
So any further question? No? Okay, so we move on to the scoring part. notice that all the scores are filled in the scoring sheet. So please raise your score for the reporter. So the scores are 8, 9, 8, 8, 8, 9, 9, 8, 8, 9, 8. And the score for the opponent is 8, 8, 6, 7, 6, 8, 9, 8, 6, 8, and 8. And the score for the opponent is, oh, reviewer, sorry. 7, 7, 7, 6, 7, 8, 7, 7, 6, 6, and 6. Okay, we are coming to the comments for the reporter. The scores are quite high, so I think we just invite any one of you to give some comments. Okay, so I will be the one to give some comments. Actually, my score is not so high. Okay, I think that actually you managing a pretty good study, but and also you observed some chaotic behavior. Okay, but the question asked about in this condition, the amplitude start to increase. Okay, so first thing I think you need to say is like why it increase. But the only reason you give us is about is the resonance. Okay, but usually in the resonance, especially in typical mechanical system, the resonance will give you a saturated amplitude. But you didn't mention anything about that. Okay. So I think that would be a pity. Okay. So I think that's something better to mention. Okay. For the opponent, we have 3, 6, 1, 7, 0, 8, and 1, 9. So for the low mark, 7, 6, and 7, any comments? Yeah, please.
I give it 6, but actually your performance is already quite good. And I just have a feeling relative to the strong report from the reporter that you should be more tougher and then find some point, sharp point. But it looks like most of the discussion stage is dominated by the reporter. It's a pity. Yeah.
Okay, so any comments for the high mark? 8 and 9?
Okay, it's my turn. Okay. Usually for opponent, we will oppose to the reporter's report. Right? Usually you think this is the way to do the opponent. But however, from my point of view, you agree with the reporter's reports, agree with their results. It's also very important. I think he did that during the discussion. So that's why I give him the time on. Thank you.
Okay. And for the reviewer, we have 1, 8, 0, 7, and 0, 6. So any comments about 7 and 6? No? Okay. Well, I think the score itself is quite even, okay? The distribution is not very big. So I can give you some comments from myself. I think you asked a quite good question. Okay, at least one of the questions is quite, to me, is quite good. the question, according to my note, is about why the system become chaotic. Okay, I think that's a good question, but to my point, the way you ask is a little bit not to the focus. Okay, you just say it's sensitive to the initial condition, but they answer this, and you just say, okay, that's okay. Actually, it's not only sensitive to the initial condition. There should be some iterational effect coming into the system. But later on in your review, I don't see you mention about that. They didn't answer this part, but you didn't raise this point. Okay, so to me, your review is kind of average review. So I think that's why no further comments. Okay, I think we have all the scores, and because we have a ceremony in the afternoon, so I don't want to announce who is the number one here, but I think that most of you already know the result. So I would like to close the final fight here, and I would like to invite everybody to give big applause to all three teams for their good performance. Thank you. Then I switch back to Chinese. 我们等一下吃中餐是在体育馆。
中正堂。
中正堂，对，在中正堂，就是斜对面那个长得像体育馆的地方。然后，但是现在有一个大问题，那边早上在上羽毛球课，上到12点10分，然后我们的工作人员就在